Alright, so in this video, what we're going to do is we're going to discuss a new circular or trigonometric function, and this one is called the tangent function. Now, if you look at your text, and in most trigonometry texts, you'll see a formal definition of the tangent function and how to compute it, and so ours is no different, but what I'm going to do here is kind of motivate what the tangent function actually is and also why it has the name. Something I don't like about the presentation of most trigonometric texts and classes even is a lack of sort of historical context into why this thing is called the tangent. So we're once again back to our favorite circle, the unit circle. And so as far as tangency goes, what you see is here's the unit circle, and over here is a line tangent to the circle, perpendicular to the x-axis. And so as usual, this distance here is 1, right? And so the way we define tangent of an angle theta is if I take some theta here, some angle, and I draw some line, right? What we create is this triangle who is a right triangle, whose base is 1, and whose height is, let's say, h for height, and that height is the tangent function. So then we could see how we get the name tangent. It's just if I go forward one step, how high do I go along this angle? All right, so let's see how one would go about computing this in this case. Well, if I want to know this height, I do have here an r, right, a radius from my origin to this point here. And that radius, by the way, is not 1, right? Because this is 1, right? This radius is 1, and so it's 1 and then a little bit more. That's this green line here. And so if I want to know what that height is, I can note that some things here. What I do know is that sine of theta is the height over the hypotenuse. Cosine of theta is the base over the hypotenuse. And so what this height is equal to, the one way we could think of this is as the height over 1. So which I could rephrase as the height over r over 1 over r, right? I'm multiplying the numerator and denominator by 1 over r. I haven't changed the value of the fraction. And so we can compute tangent as sine theta over cosine theta, right? And that's how we would, in general, compute the tangent of an angle. And so if you wanted to, if we moved off of the unit circle for a minute and we were just given some right triangle, I don't like that. Alright, let's say we're given a right triangle, and let's say the radius is r, the height is h, the base is b, and we have an angle theta. Then the way we could see what the tangent is, well, if I restrict it to 1, or even better yet, let's not restrict that to 1. I'll travel up 1 and drop down a right angle here. This base is going to be cosine theta. This height is going to be sine theta, right? And so what we know about the red and green triangles in this instance is that this smaller interior triangle and this larger exterior triangle are similar, as we've seen before. And so the ratio of the sides are preserved. And so what we have then is that sine theta over cosine theta, that's equal to h over b, and that's by definition tangent theta. And so what we can see is if you're just given some triangle, we can find the tangent of some angle as the height over the base. Now, there is a different way to think about this, which isn't always presented in a lot of trigonometry texts, which I find really useful and enlightening, and that is when we have this height over this base, right? This is some y value, right? That's going up and down, and this base is some x value going from left to right. And so one way to think about this height over this base, we've seen things like that before. It's the slope, right, of this line. If we were to extend this line out, this height over this base would be the slope of that line. And so one way I like to imagine tangent is also as the slope of the line or ray induced by theta. Alright, and so let's kind of see what this looks like in general. So here we have a plot of the unit circle, and alright, there we go. We have our tangent line here, right? Our angle is at 0 radians, and here we have our unit circle. So what's going to happen as I start increasing my angle theta here is that naturally my height increases, right? And so as I continue along the circle, the height increases. And the more I increase the angle, the higher my height goes. None of that is particularly surprising. But you may notice, though, that this line is curving upwards as positive concavity, which means it's growing faster and faster. And that's because, there is no limit to how high this tangent function could go. I could zoom all the way out here, go to 30, draw a line down to the origin, and there would be a perfectly good angle over there, right? So at some point, every subsequent increase of the angle or the number of radians of the angle results in bigger and bigger changes in the height of where it hits this wall. And so you might imagine it shoots up and up and up and up and up, right? And so let's see what happens once we hit pi over 2. Once we hit pi over 2, we'll notice that I don't have a line here, right? I don't have a line drawn. And that's because that ray is now parallel to the line of tangency. And since they're parallel, there's no point of intersection. There's no point of intersection. There's no tangent value. Alright, so what happens if we go just a little bit over pi over 4? Let's say 1.6. If I go just a little bit pi over 2, then I'm off a little bit, and now I'm no longer parallel, so I'm shooting down all the way here, right? And just like there is no upper bound to tangent, there is no lower bound either, because I can go far down on this line as I want, shoot a ray up through the origin, and create a valid angle. And so it goes up to positive infinity, and then back down to negative infinity. And then let's put it in at pi, at exactly pi, now the ray from your point on the unit circle to the tangent line, that ray, it lies exactly on the x-axis. So it intersects the line of tangency at height 0, so we're back to 0. And then notice that it's going to repeat itself from here, right? What's going to happen now, so let's say 3.15, it's going to, we shift a little bit, it's going to pop up a little bit, and it's just going to repeat what we did before, right? Because now I'm shooting up back through the origin to the line of tangency, so I'm going to repeat itself. So I'm going to repeat, myself. Right? So if I were to draw just what tangent looks like, we would get something like this, right? It goes, let's say from the origin up to positive infinity if I raise my angle up, down to negative infinity if I lower my angle down, and it repeats itself. But it doesn't repeat itself the way sine and cosine do every 2 pi units, because what it does when your angle is, or when your point on the circle is in the upper hemisphere, is mirrored by what it does in the bottom hemisphere. So once it goes from 0 to pi, that's a full cycle, and then pi to 2 pi, it repeats itself. So instead of periods of length 2 pi, you're looking at periods of length pi. So what we saw, for example, is if I drew x equals pi over 2, we saw that there was a point of tangency there, right? And if I were to bump it up by pi, right, 1 period later, I get the asymptote there, right? So those are vertical asymptotes because tangent's not defined at those values. At those values, what you have are rays that are either shooting straight up or rays that are shooting straight down that don't intersect the line of tangency, so they don't have values there, so we get these asymptotes. And what you can see here is if I say minus 10, minus 9, 210, there we go. If I were to draw in a couple more of these lines of tangency, then we could see this repeating period, right? So it goes from pi over 2 right here, plus another pi, plus another pi, plus another pi, minus a pi, minus a pi, minus a pi. And so this is a description of what the tangent function is, why it has that name, and different ways to compute it. One way is to say that it's sine over cosine, and the other way is to say that it's the height over the base, and these are equivalent to each other. Alright, thank you very much, and as usual, if you have any questions or comments, please email them to me or post them in the discussion board, and I will see you in the next video. Thank you.